Okay, this is example 12.2 from Discovering Design with Chemistry. And yay, we now have some rules for determining oxidation states, so we do not have to draw anymore little Lewis structures or whatever. So we're going to use the different rules and look through how to use them in these examples. What are the oxidation states for the atoms in S8? So S8 means that we've got just one thing, and it's not an ion, it's just an element. So rule 2 is going to apply, and that means the oxidation state for S is 0. The next one, what are the oxidation states for the atoms in Al2S3? So if you look at the periodic table, which I don't have up, but I have one on my wall, and you probably have one in your book, aluminum's in the metals, sulfur's in the nonmetals, and so we've got an ionic compound here. And so because it's an ionic compound, we can just use their charges. Let's see, so Al would be 3 plus, and then sulfur, it would be 2 minus. So that's kind of similar to the first one in example 12.1, but we're, just reviewing here. All right, what are the oxidation states for the atoms in H2S? So this is a covalent compound because both of these are nonmetals, and so we need to use a different rule. So we can look at rule number 5, which tells us in covalent compounds and polyatomic ions, H has an oxidation state of +1. So we have a +1 state, but there are 2 of them, which means we have 2 plus. And we know that we don't really have a rule for S, but we know from rule 3 that the total charge, the oxidation states must equal the total charge. And this H2S does not have a charge, which means the sulfur has to balance out those 2 pluses with 2 minuses. So H is 1 plus, there just happen to be 2 of them, and S is 2 minus, there's only 1, so it carries all of that. All right, so and you notice that sulfur has changed oxidation states because at the top, the first problem was 0 and now it's 2, so it depends on where it is. Let's look at the other problems. What are the oxidation states for the atoms in CH3F? Again, this is another not ionic compound thing, and we don't have rules for all of these, so we're going to start with what we do know. So there's no rule for C necessarily, but we know that H is usually going to be a +1 charge because of number 5. And we have 3 H's. And then fluorine is -1 in any compound. So we have 1 negative here. And we know this overall thing has to make 0. And so we need to have everything balance out. We have 3 pluses and 1 minus that we're working with so far. And so we need 2 more minuses to balance out this. And so let's go ahead and write the ones we know before we get confused. So hydrogen's 1 plus and fluorine is 1 minus. And then to make this balance, we need 2 more minuses for I should put these side by side so you can tell they're both the same thing. 2 more minuses for that carbon to make sure it balances out. So carbon is going to have a 2 minus in this particular one. And to get through that one, we started with rule 5 to find hydrogen, then we went to rule 4 to find fluorine, and then we used rule 3 to finish it out. All right, so the next one is, what are the oxidation states for the atoms in NaNO3? You might recognize this as being sodium plus a polyatomic ion. In other words, this is an ionic compound. And so sodium is in our first column, so that has a 1 plus charge. So we can go ahead and just label that. So there's our 1 plus. And we know that this as a whole is a minus charge, but we have to break it up into its pieces. So let's look at so this is a 1 minus for NO3. So let's look at its different pieces. So we don't really have a rule for nitrogen, but we do have a rule for oxygen. And that is that in most compounds, this is rule number 6, that it has an oxidation state of 2 minus. And so this is 2 minus. But remember, there are 3 of them. So we have, actually, let me put this side by side. So it's like there's 1 oxygen, there's another oxygen, there's another oxygen. And we need the overall charge to be -1 for this. So how many pluses will we need to stick up under the nitrogen to balance that out the 6 negatives so that we have 1 minus, we would need 5. And there's only 1 nitrogen, so all 5 would be for that 1 nitrogen. So our oxygen is 2 minus. We got that from rule 6. And then our nitrogen we just figured out based on the other things, and that's 5 plus. And then our last problem in this section says, what are the oxidation states for the atoms in S2Cl2? All right, so this is not an ion composed of only one atom, and it's not an element or homonuclear molecule. It doesn't have, we don't know the charge of either one yet, so we can't start with rule 3. It's not fluorine, it's not hydrogen, so we're going to have to go with the usually true and go with the group 7A elements, especially chlorine, usually have an oxidation state of 1 minus. So we're going to go ahead and say that chlorine is 1 minus, and we'll put 1 minus for each of those 2 chlorines. Well, for sulfur, that means to balance this out, now we're using rule 3. This whole thing has no charge. So to make it balanced so that it has 0 charge as a whole, sulfur, each of those sulfurs must have one of those pluses. So sulfur is 1 plus. So notice that sulfur changed oxidation state in several of our examples, and it mentions in the next part of the chapter that you'll read that a lot of atoms can have at least 2 different oxidation states. Some of them have more than 2, and a lot of reactions are based on that idea. Anyway, so the rules for determining oxidation states start with ones that are always true, and if you can't find anything that matches one of those, go to the usually true next. Break everything in pieces. What do you have a piece of that you can figure out what's left over?